Hello everyone. So today I would like to extend what we did in our last lesson, which was the equation of a line, and extend that now to the idea of how do we find the equation of a plane. It's the same idea. Whenever we have the equation for a line or for a plane, the idea is that we need some way to be able to describe all of the points. And in this case, instead of just a line, we're now trying to describe all the points that are on a plane. When we try to draw 3 dimensions and 2 dimensions, it's always a little bit tough to see, but hopefully in my diagram here you can see we have our 3 axes, x, y, and z for 3 dimensions. And then usually when we try to draw a plane, although this plane would extend in all directions here, what we do is we try to draw a rectangular shape of some sort here. I've drawn a parallelogram that's trying to show that that plane is sort of cutting through here, and I tried to draw the dashed line there that we see that that plane is cutting through the x-axis and then would continue to extend in all directions. To build the vector equation for a plane, it's basically the same idea as what we do when we're trying to find the vector equation of a line. So what we're trying to do is to be able to describe any point P that I've put on here with coordinates x, y, and z. So to do that, what we first need is some initial point that is on the plane, a starting point, very similar to what we did with a line. So I'm going to put that point Q right here and say there is our initial point on this plane. And what we see then is that to identify that point using a vector, what we do is we use position vectors. That position vector would then point to that spot or that point that is on the plane, and that it would have the exact same ordered triple. So our position vector pointing to this point Q on our plane has the exact same ordered triple, and we can draw that in there and say, well, there is that position vector that is pointing then to the point Q on the plane. Second part now is that once we have that initial point, what we want to be able to do is we want to be able to move to any other point that is on the plane. So I can move this point P anywhere on this plane. So how do I move to that point? So unlike a line, it's slightly different. What we need to do is we need to define now 2 non-collinear direction vectors instead of just one. If I'm going to be able to move on this plane, which essentially has 2 dimensions to it, I need 2 direction vectors to be able to move in this 2-dimensional plane. Non-collinear simply means that they just can't be pointing in the same direction. So I'm going to say, well, let's call that my one direction vector. So I'll call that A. And I'll put another direction vector on here, which I will call, let's do this, we'll call that one B. So I have these 2 direction vectors A and B on this plane. And then notice that if I want to move from Q to any other point that is on the plane, so if I want to move from Q to P, okay, we've seen this before when we were doing a vector addition. I can do this by saying, well, I can do some scalar multiple of B, and I can do some scalar multiple of A, and there's our vector addition using our triangle law. So I'm going to say that I have t times b, some scalar multiple of that. I don't know what t is, but I need some multiple of b, and then I would need some multiple, so I'm going to say SA. I need some multiple of vector A, and that will get me to that spot. And if you want, we could actually use our parallelogram law. We can come that way, or we could also come this way and do the exact same thing. Okay, so it doesn't matter which way we travel. Okay, we can either travel this way or this way, but it's some multiple of these 2 direction vectors. In other words, we can say then to get from Q to P, we're going to use some multiple of vector A plus some multiple, sorry, squeeze that in there, some multiple of vector B. So SA plus TB gets us to P. Now, how do I describe any point that's on the plane? Well, we can now use this idea to describe every single point. In other words, to get a position vector that will point at P, so OP, so if I want to describe that point really with vectors, all we do is we take a position vector and we point it at that point. So if I have that position vector now pointing to that spot, OP is really just O to Q. So I can move to my initial point, and then from there I can move from Q to P. Again, if we follow that path, we can see that OP is the same as O to Q, Q to P. So that would be able to describe that position vector OP. But we have a way to describe OQ. OQ is just that initial point that is given. And I have a way to describe QP. QP is the combination of those two direction vectors, using our triangle law to get there. And there's how we would describe then every single point that is on the plane. So in general then, if we're given an initial point and two non-collinear direction vectors, the vector equation for the plane then would be the resulting vector, which is our initial point or initial vector, plus a scalar multiple of those two direction vectors. Or if we want to write this out in full, we can say every point x, y, and z is equal to the initial point that's on the plane plus some combination of those two direction vectors. And there it is written in full. Now, similar to our line, once we have our vector equation, I can also write this in its parametric form. Parametric just means that we're going to separate out the x. Keep in mind that we now have two direction vectors. So now it looks something like this here. My y component, so y0 plus a2s plus b2t, and my z component z0 plus a3s plus b3t. And again, like our last lesson when we did the vector and parametric equations for a line, we see that here is our initial point. Okay, as this all plays out, so our initial point slides in there. And now we have two direction vectors. The one is here, and the other one is here. So very similar to the vector equation of a line, the only difference here is that to find the vector equation of a plane, we have to now have two direction vectors. For a line, we only needed the one. For a plane, we now need two, and we need two direction vectors. Again, the idea is because we're moving in two different directions on this plane, so we need two direction vectors to do that. If we look at a couple examples, so find the vector and parametric equations of a plane containing a point and a line. Okay, there's actually four ways, we'll get to this in a second, how we can define a plane. One way is to have a line and a point. If you think about that, if I have a line, if I use my pen as a line, and I set a plane on top of that, that plane could wobble. So there's many planes that would contain that line. But as soon as I say it has to contain some point over here, that would then stop that from wobbling because it now has to sit on the line, but it also has to contain that point. So that is one way we can then describe a plane. As we set this up, it's much like what we were doing the other day for a vector equation of a line. I need an initial point. Well, if that point is on the line, we can say then 3, 4, 0 is the initial point. I need a direction vector. Well, now for a plane, we need two direction vectors. So my direction vectors are A, and we can really just steal the one direction vector right from the line. So there's my one direction vector. If this line is on the plane, this direction vector would also be on that plane. And now I need a second one. And what I want to look at here is the idea that, yes, this point was on the plane, but this point here was also, so we could have used this point here as well. That point on the line, since the line is on the plane, that point is also on the plane. So if both of those points are on the plane, I'm going to just call this point B, then if I want a second direction vector, I can just use a point-to-point vector, and I can say my second direction vector is the vector that goes from A to B, because this point is on the plane from this line, and this point is on the plane. So if we do that, we end up with our direction vector -2, 6, -5. So I can then say, well, if I want my vector equation then, okay, it's our initial point, 3, 4, 0, plus some multiple of our first direction, 1, 3, 2, plus some direction, or some multiple of our second direction vector, -2, 6, -5. And there's our vector equation. If we want our parametric equation, very similarly to what we did with our line, all we have to do is just separate the x, the y, and the z. So my x is 3 plus 1s minus 2t. My y is 4 plus 3s plus 6t. And my z is 0, so I don't need to write that. 2s minus 5t. So there's our vector and our parametric equation. Now, that's one of 4 ways we can define a plane. Okay, that is this option here, a line and a point that's not on the line. We could also do this with 3 points. Again, if you think of having 3 points, if I use my fingertips as 3 points, that would define a plane, okay, because that locks that plane in place. There's no other plane I can draw if those 3 non-collinear points are on the plane. We could have 2 intersecting lines. If I have 2 lines, doesn't matter how I tilt them, we could set a plane on top of those 2 lines, and that would define a plane. Or the other way is if we have parallel lines, we just have to be careful that they are distinct. Okay, parallel and distinct means they are not on top of each other, and depending on how I rotate those 2 parallel lines, we could then sit a plane on top of those as well. And all 4 of those versions would be ways that we could clearly define what plane we are talking about. In each case, you'd have to be a little bit careful about how you're getting this information. If I had 3 non-collinear points, my initial point would be easy. My direction vectors, I would have to do a couple point-to-point vectors using the points that are there. This one we saw. If I had 2 intersecting lines, it's actually one of the easier cases, because if I have 2 intersecting lines, I'm going to have 2 equations of lines, which means I can take the direction vector from the one line, I can also take the direction vector from the second line, and then I would have 2 initial points that I could pick, either from the first line or the second line. 2 parallel and distinct lines, I'm going to look at an example right here. Here are 2 parallel and distinct lines. I know they are parallel because I can look at their direction vectors. And I see that they are scalar multiples of each other. If I multiply this by -2, I would get this direction right here. So they have the exact same direction, which means they are parallel. I know they are distinct because the 2 lines have different initial points. So they're pointing in the same direction, but they have different initial points. So how do I get 2 direction vectors here? Okay, I'm not finding the whole equation. This question just says find the direction vectors. So one is really easy. Okay, they share this direction, so we can pick whichever one we want. However, I now need a second direction, so I can't use both of these because they are pointing in the exact same direction. So as a second direction vector, what I'm going to do is just realize that they have given me 2 points that are on the plane. They've given me a point from the first line and a point from the second line, so I can use that point-to-point vector idea again. So I can say my second direction from A to B, if we subtract this out, will give us then a direction of 1, 1, and 1. 4 minus 3, 3 minus 2, 2 minus 1 as we do our point-to-point vector. And now we have 2 directions. Okay, we could steal whichever point we want as our initial point, and if the question had asked us for the equation, we could go ahead and then write out those equations. The last piece that I want to finish with then is back to what we call our Cartesian or scalar equation. We saw in 2 dimensions we had a scalar or Cartesian equation of a line. Originally in grade 9 we would have called that our standard form. We said there is no standard form for a line that's in 3 space, and that's because in 3 space when we write out the Cartesian or scalar equation we actually get a plane. We define this in a very similar way using this idea of a normal vector. So a normal vector to a plane would be then any vector that is perpendicular to the plane. So in 2 dimensions we can easily draw a vector that is perpendicular to the line. In 3 dimensions we can draw this vector that would be perpendicular to that plane. And what we should see is that if I draw on my 2 direction vectors, that means that this would also be perpendicular to both of these direction vectors. You can see that clearly I've drawn my symbol here, we're perpendicular to this, but we could also do this here. If we are perpendicular to the plane, it must be perpendicular to both of those direction vectors. And if that is the case, then if we have this normal ABC, which is perpendicular to this plane, then our Cartesian equation would be AX plus BY plus CZ plus D equals 0. Looks much like our standard form in 2 dimensions, which gives us the equation of a line. Our Cartesian or scalar equation, if I put this into 3 dimensions, I'm adding what extra term in here, and we no longer get a line for this. This actually now defines a plane instead. So quick example then, how do I come up with that equation? So if I have my vector equation, determine the scalar Cartesian equation, I start in much the same way. I'm going to say that I have an initial point. My initial point here then is 3, 4, 0. I have direction. We can just take it straight out of the equations. I have that my one direction vector is 1, 3, 2, and my other direction vector is -2, 6, and -5. Now, to come up with my Cartesian equation, what I need to know is what is the normal. So what I need is a vector that is perpendicular to the plane, or as I was starting to say here, it is perpendicular to the 2 direction vectors. And this is where it's nice, the skills that we have learned. How do I get a vector that is perpendicular to 2 other vectors? Well, that is the definition from our cross product. So the normal is really just the cross product of our 2 direction vectors. So we see how these skills from our previous lessons start to come into play here. If I do that cross product, that means that I am going to do the cross product between 1, 3, 2, and -2, 6, -5. I've gone ahead and done that. So if you do this, you'll get -27, 1, and 12. I'm going to choose, and we need to be a little bit careful here, because if we think about how this is going to fit into our equation, that's our ABC, there's our ABC. Whenever we write something that is in their Cartesian or scalar form, we always want this first term to be positive. So I would look to reduce this if possible. This doesn't reduce, but I will change the sign here. So I'm going to multiply everything by -1 so that I choose that to be positive, -1 and -12. If we fill that into our equation then, we would then have 27x minus 1y, so minus y, minus 12z plus d equals 0. Very similar to what we did with the Cartesian equation for a line. I now have an initial point that is sitting on this line, so we can now sub in x, y, z as 3, 4, 0, which would give us 27 times 3 minus 4 minus 12 times 0 plus d equals 0. If we solve for d, we would end up with -77. So therefore, our scalar equation would be 27x minus y minus 12z minus 77 equals 0. So there's the 3 versions that we deal with as we look at the equation of a plane. Now, as we finish up, I realized that I missed one thing on the first page. As we were flying through this, we found out how to get the vector equation and we wrote it out, but I had put in one extra note here. Planes are typically denoted by. Interesting, when we want to label a plane, what we do is we actually use the symbol pi. And if we were looking at multiple planes, then I'd use a little subscript and it'd say this is plane 1, or we'd use pi 1 to represent that. Okay, so a little side note, if you ever see that in the textbook or in other literature, mathematical literature, we often use that symbol pi to represent planes. That's our note. If you have any questions, please let me know. Otherwise, there's some assignment questions there to try. And this actually finishes off all of our vector topics. So let me know where you're at and if there's any questions. Have a good day, guys.